The impact came without warning. Before any sound, an explosion opened a crater several meters wide in the Staveley Road neighborhood of London on the afternoon of September 8, 1944. Residents ran without knowing what had struck the street, because no aircraft had been seen flying over the city at that moment. The complete absence of noise prior to the explosion confused even the emergency crews. The British technicians who arrived at the site noticed twisted metal fragments, pieces of light alloy, and remnants of melted cables. Nothing there resembled the conventional bombs dropped by aircraft. The destruction indicated that the projectile had crossed the atmosphere at high speed, hitting the ground before any defense had time to react. The initial analysis showed that the weapon had come from above on an almost vertical trajectory, traveling at an estimated speed of more than 5,000 kilometers per hour, enough to break the sound barrier while still in the air. That speed rendered sirens, radars, and anti-aircraft batteries useless, because no British system could detect or intercept something that reached the ground before it could even be heard. The explosion marked the first operational use of a ballistic rocket in history. The missile, launched from occupied Holland, had traveled about 300 kilometers before hitting London. The distance and behavior of the projectile revealed that it was an entirely different type of weapon from those already used in the war. It did not come from an aircraft, did not follow a visible trajectory, and left no time for evacuation. As the debris was examined, intelligence teams realized that the weapon contained components that matched nothing reported in previous months. The shape of the metal plates, the fusion of materials, and the fragments of valves suggested a type of engineering not seen in any known aerial bomb. The logical inference was that it had been designed to fly far beyond the reach of any pilot. This first impact exposed to the British the existence of a project that had been under development for years inside Germany, far from any outside observation. Before new analyses could be completed, another projectile struck London the same day, repeating the pattern of vertical descent and instantaneous destruction. From that moment on, it became clear that the weapon was not an isolated one. It was part of an entire line of development that had begun long before the attack, in German facilities specifically prepared to create vehicles capable of crossing continental distances. The creation of this missile involved dedicated laboratories, entire engineering teams, and testing centers built exclusively for that purpose. Long before the impacts in London, Germany had already been exploring the possibility of using rockets as long-range weapons. This initiative began in the early 1930s, when the Army sought alternatives to heavy artillery, which was limited by range and difficult to transport. The idea was to create a projectile capable of crossing borders without relying on gigantic cannons. To begin these studies, the Army allocated a forested area in Kummersdorf, south of Berlin. The facilities were small, consisting of simple workshops, an improvised test field, and a few metal benches for experiments with liquid propellant. The site had originally been created for ammunition testing, but ended up becoming the initial center of German rocket research. Among the young men recruited to work there was Werner von Braun, newly graduated and already interested in rockets since adolescence. He found an environment where engines were assembled experimentally, using ethanol and liquid oxygen. These engines were rudimentary, but powerful enough to require constant reinforcement of the structures that supported them. The first tests revealed immediate challenges. Combustion chambers cracked from excessive heat, and intense vibrations caused metal supports to deform after only a few seconds of operation. Each explosion left marks on the hardened ground and forced the team to rebuild entire sections of the test stands before trying again. As experiments advanced, the Army sent in new engineers specializing in metallurgy, electronics, and automatic control. The workshops became busier, but Kummersdorf's infrastructure remained limited. The proximity of the forest created fire risks whenever hot gases escaped the engine during failures. The base itself had to be evacuated on several occasions when flames spread quickly through the dry vegetation. In addition to the safety issues, the physical space was insufficient for testing larger prototypes. Engineers were already planning rockets that would require open areas, long access roads, and specific towers for instrumentation. In Kummersdorf, any expansion would have meant demolishing existing structures or attempting to extend operations into areas that were not authorized for military use. With the increasing size of the engines and the volume of propellant needed for each test, the officers in charge concluded that Kummersdorf could not keep up with the pace of the project. Internal reports indicated that continuing the program required an isolated site with access to the sea and enough open space to build a modern and safe facility. This need paved the way for the creation of an entirely new center. The Army began searching for land that would allow for high-power tests, the construction of hangars, and the installation of advanced measurement systems. This search would lead the team to the Baltic coast, where the next chapter of the rocket program would grow to an industrial scale. The search for a site capable of supporting large-scale tests led the German army to the Baltic Sea coast, on the island of Usedom. The region offered something Kummersdorf could never provide: open space, natural isolation, and the possibility of aiming test engines toward the sea, where the hot gases dissipated without risking nearby homes. This combination made the location the chosen site for the new development center. Construction began in 1937, transforming an almost deserted area into a modern research complex. Metal workshops, hangars, and laboratories were built at a rapid pace, creating a set of facilities dedicated exclusively to the study of rocket engines. Internal roads allowed the transport of large components without relying on improvised trails. The structure grew enough to host wind tunnels, instrumentation rooms, and measurement towers installed along the coast. These instruments allowed vibration, thrust, and stability to be recorded with greater precision than in any other German facility. The amount of data collected in the first months surpassed everything previously produced in the program. With the new workshops, the team began manufacturing prototypes that required complex welding processes and metal alloys specifically designed to withstand high pressures. Fuselage sections were assembled in modules and transported by rail to final integration areas. The scale of work increased so quickly that newly arrived engineers needed specific instructions just to find their assigned sections within the complex. The site also enabled real flight tests. Ramps were built at the northern edge of the center, allowing rockets to be launched toward the open sea. These launches revealed unprecedented problems, such as instability during ascent and failures in the gyroscopic control system. Each test resulted in new adjustments to actuators, materials, and assembly procedures. In addition to testing, the Baltic coast favored the storage of large quantities of liquid oxygen, essential for propulsion. Cryogenic tanks were installed near the engine stands, ensuring a constant supply for extended trials. This infrastructure existed nowhere else in Germany and made it possible to explore ranges and power levels never before tested. The growth of the center attracted specialists from various military sectors, including officers who saw in the rocket program an opportunity to create a long-range weapon capable of bypassing enemy defenses. These visits resulted in frequent meetings in which scientists presented technical data on pressures, speeds, and structural failures observed in the prototypes. As research progressed, it became evident that the project was no longer experimental. The workshops began producing components in series, and entire teams dedicated themselves solely to calibrating automatic navigation systems. The site became the heart of German rocket development, and the base where the model that would become the V-2 took full shape. With the Peenemünde facilities operating at full capacity, the engineers began building a sequence of experimental rockets that would serve as the basis for a long-range model. The first of these, known internally as the A3, was assembled to test concepts of stability and propulsion on a platform larger than anything that had been used in Kummersdorf. It was a simple vehicle, but large enough to reveal problems that smaller engines had not shown. Tests of the A3 revealed significant failures in flight control. As soon as the rocket left the ramp, small oscillations amplified rapidly, diverting the vehicle from the planned trajectory. The gyroscopes available at the time did not have adequate sensitivity to correct abrupt movements, and the control surfaces responded with delay. These results indicated that the design would require a complete revision of the guidance system. To solve these problems, the team developed a test model called the A5. It was smaller and allowed individual components to be validated without risking larger vehicles. The focus was on aerodynamic behavior and the accuracy of navigation instruments. A5 launches began to produce more reliable data, allowing engineers to identify the limits of the materials used in the fins and fairings. These trials showed how the rocket reacted to variations in temperature, altitude, and speed. On windy days, the sensors required recalibration. On longer flights, deformations appeared on external surfaces due to heating. Each record helped adjust manufacturing parameters and determine which metal alloys would withstand the dynamic pressure of a larger rocket. With this accumulated data, the engineers began building a much more ambitious prototype, called the A4. This model surpassed all previous ones in size, weight, and power. It stood more than 14 meters tall and had a combustion chamber capable of producing enough thrust to carry a warhead hundreds of kilometers. The scale required new test stands reinforced with concrete and large metal structures. Integrating the A4 systems brought unprecedented challenges. The engine had to be equipped with fuel pumps powerful enough to pressurize ethanol and liquid oxygen in a constant flow. The hydraulic actuators responsible for moving the fins received millimetric adjustments to ensure stability during ascent. Each component depended on another, forming a system that would only function if all parts achieved high precision. When the first A4 units were ready, Peenemünde entered a testing phase that involved entire teams dedicated to instrumentation, control, and data recovery. The rockets were positioned on open-air launch ramps, and measurement lines were set up in protected cabins near the coast. Whenever a launch was authorized, operators monitored pressures, temperatures, and vibrations in real time through electrical panels that covered entire walls. The initial flights still showed failures. Engines shut down earlier than expected, and some vehicles broke apart during ascent. Each incident was investigated carefully because it revealed where the design needed adjustment. These tests generated a volume of information that finally allowed engineers to stabilize the A4's behavior during complete flights from start to finish. With the A4 reaching altitudes and distances far greater than those of the previous prototypes, the program ceased to be merely a scientific experiment. The rocket now possessed characteristics that drew the direct interest of military command, which began monitoring each advancement closely. From that point on, the project began receiving growing expectations and pressures that would influence all subsequent stages. As the A4 demonstrated the ability to reach great altitudes and distances, the Peenemünde Center began receiving frequent visits from military authorities. Interest grew because the tests indicated that the rocket could deliver an explosive payload to regions that German aircraft could no longer reach safely. This new scenario brought the project closer to Army sectors responsible for strategic weaponry. With this closer involvement, military groups began to attend technical meetings that had previously been restricted to engineers. Artillery officers sought to understand how the rocket could be integrated into the existing arsenal, while Luftwaffe representatives evaluated whether the technology would compete for resources with aircraft projects. The presence of these sectors created discussions that went beyond engineering. The administrative structure of the program changed when authorities linked to the SS showed interest in taking control of part of the production. The official justification was to accelerate development, but this transfer of influence altered the routine at Peenemünde. New supervisors began requesting detailed reports on deadlines, supplies, and test performance, placing pressure on technical teams already dealing with frequent failures and constant adjustments. This accumulation of authorities with differing expectations produced conflicts over priorities. Some groups argued for increasing the number of test launches, while others demanded that production begin as soon as possible, even before all failures were fully understood. This divergence created unstable schedules in which stages were moved forward or delayed according to decisions made outside the laboratory. In addition to disputes over timelines, debates arose concerning the weapon's exact function. Part of the High Command wanted to use the rocket as an instrument of retaliation against enemy cities, while other sectors tried to assess its tactical usefulness. This uncertainty influenced the project's design itself, because it determined the type of warhead, the desired range, and the pace of production. The increase in external pressure also affected the internal work environment. Engineers began reviewing components under strict targets, often adjusting systems that still required deeper study. The accelerated pace raised the risk of failures and made it necessary to expand teams dedicated to investigating incidents during open-air tests. With every new test, representatives from different military sectors sought information directly from instrumentation operators, attempting to influence decisions regarding adjustments and future launches. This interference fragmented communication between technical departments and multiplied meetings that consumed time previously dedicated exclusively to development. With so many parties competing for control and direction, Peenemünde no longer functioned as an isolated laboratory. The center had become a strategic point for the German command, and each technical advance triggered new claims over who should coordinate the program. This situation created an environment of constant tension, which would intensify even further when external events directly affected the complex. While internal disputes shaped the pace of the program, British intelligence services were analyzing reports from the European resistance that mentioned unusual facilities on the Baltic Sea coast. Aerial photographs obtained by reconnaissance missions showed structures that did not resemble conventional factories. The images revealed tall towers, long warehouses, and pathways converging toward platforms facing the sea, raising suspicions about the nature of the work conducted there. The British government began to consider Peenemünde a possible research center for advanced weapons. After weeks of evaluation, it concluded that a bombing operation could delay or interrupt a project whose purpose was not yet entirely clear, but seemed significant enough to justify a large-scale offensive. The Royal Air Force prepared a night mission with dozens of heavy bombers. On the night of August 17, 1943, British aircraft crossed the Baltic and directly struck the Peenemünde facilities. The first explosions destroyed part of the workshops where A4 components were assembled. Warehouses housing machine tools were set ablaze, and entire sections used to calibrate navigation systems were reduced to rubble. The attack also hit residential areas used by engineers, technicians, and workers. Buildings near the test tracks collapsed under the impact of high-caliber bombs, and support teams had to evacuate multiple zones of the complex. Personnel losses included experienced members who had direct involvement in engine assembly and test rocket construction. The power lines that supplied measurement instruments were damaged, interrupting all ability to record test data. Underground cables used to transmit telemetry signals were cut, preventing the center from conducting launches until minimum repairs were completed. This interruption compromised the planned schedule for validating adjustments to the A4. At dawn, the teams that survived the attack began assessing the state of the facilities. Many areas required complete reconstruction because metal structures had been deformed by the heat of the explosions. Components under development were lost, and numerous precision instruments became unusable due to vibration caused by the detonations. The partial destruction of the complex forced the German command to reconsider the production site. Peenemunde's vulnerability had become evident, as further attacks could interrupt the program indefinitely. Based on this assessment, authorities decided to transfer rocket assembly to underground facilities located in the interior of the country, where bombings would be less likely. With this decision, the technical team had to reorganize the workflow. Files, parts, and machines were separated for immediate transport. The Baltic Coast Center would continue to be used for testing and research, but large-scale production would be relocated to an area protected by mountains and excavated tunnels. This change marked the end of the phase in which Peenemünde concentrated all stages of the program. The continuation of the rocket now depended on a completely different environment, one whose infrastructure had originally been designed for mining rather than the manufacture of ballistic weapons. The transfer of production brought the program to the mountainous region near the city of Nordhausen in central Germany. The area contained tunnels excavated before the war for mining, forming an underground labyrinth with kilometers of interconnected galleries. These structures offered natural protection against bombings, something Peenemünde could not guarantee. Authorities ordered the immediate adaptation of the galleries to function as a factory. Machine tools, metal workbenches, and measuring equipment were transported by train to the tunnel entrance. From there, smaller locomotives distributed the items through narrow corridors where teams attempted to organize assembly sectors in spaces originally designed only for mineral extraction. The underground configuration required changes to the manufacturing process. Rocket sections had to be assembled in smaller modules because the available space limited the movement of large parts. Each module followed internal tracks to areas where engines, tanks, and hydraulic systems were sequentially attached. This method created an unusual production line, but one suited to the physical constraints of the site. The dim lighting of the tunnels affected the work pace. Lamps hung at irregular intervals left entire areas in semi-darkness, complicating visual inspections of sensitive components. To compensate, technicians installed additional lighting above critical workbenches, especially where fuel valves and guidance system elements were assembled. Ventilation also needed adjustment. Test engines released hot gases and particles that accumulated quickly in the galleries. Industrial fans were placed at strategic points to push contaminated air out of the mountain, but the airflow was not uniform. In certain sections, workers had to halt operations until air renewal was sufficient for work to continue. Internal movement of parts required the creation of a custom logistical system. Wagons transported metal structures still in raw form, while smaller locomotives carried finished components to inspection. This traffic had to be precisely coordinated because the tunnels allowed passage in opposite directions only at specific points where double tracks had been installed. The underground environment also revealed limitations in the testing process. Peenemünde had open-air stands where vibration and gas flow dissipated naturally. In Nordhausen, engineers had to develop special mounts to test engines without compromising the stability of the galleries. Each trial required careful monitoring to avoid damaging the mountain's internal walls. Despite the difficulties, production reached a volume sufficient to supply military units responsible for launching the rocket. Completed sections left the factory in covered wagons, traveling along railways that crossed the interior of Germany. These trains had to operate under restricted communication because any interruption along the route endangered the delivery of projectiles to launch bases. The move underground marked a decisive point in the program's trajectory. It no longer depended on vulnerable facilities and began operating within a structure protected by hundreds of meters of rock. This change allowed production to continue even as the advance of Allied forces pressed into German territory. The continuation of underground production required a constant flow of materials from various regions of Germany. To assemble a single rocket, it was necessary to gather aluminum alloys, precision electrical systems, hydraulic pumps, and tanks capable of storing hundreds of liters of ethanol and liquid oxygen. Each component depended on an industrial chain already under strain from the prolonged war. The metal alloys were shipped from factories specialized in treating aluminum to withstand intense vibration. The material arrived in plates that underwent cutting, bending, and welding processes inside the galleries. The thickness of these plates had to be uniform because any variation would compromise the fit of the rocket's conical sections and affect its stability during ascent. The propulsion system depended on high-rotation pumps capable of pressurizing fuel and oxidizer without failing at high altitudes. These pumps were produced in small batches by industries that also manufactured aircraft parts. The direct competition for production capacity forced factories to redistribute employees and machinery among sectors competing for military priority. The most sensitive element in the logistics chain was the production of liquid oxygen. The rocket consumed large amounts of this oxidizer, which needed to be kept in cryogenic tanks until the moment of launch. Producing liquid oxygen required specialized industrial facilities with compressors and cooling systems that consumed significant amounts of energy at a time when German power plants were already at risk of interruptions. Electrical components came from factories concentrated in southern Germany. Gyroscopes, cables, and relays were packed in reinforced boxes and shipped by train to the station closest to the mountain. These components needed to be inspected before installation, because vibrations during transport could alter the calibration of sensors responsible for keeping the rocket stable during flight. The railway network supplying Nordhausen faced constant interruptions due to Allied bombings. When main lines were damaged, trains were rerouted onto secondary tracks that increased travel time and reduced delivery frequency. Each delay forced underground teams to reorganize shifts, prioritizing modules that still had parts in stock. The program's industrial consumption also included simple materials, but in large quantities. Kilometers of electrical cables were used to connect sensors, actuators, and ignition systems. The underground workshops required constant welding, which demanded frequent supplies of electrodes and industrial gases. These items were stored in improvised depots beside internal tracks, from which they were distributed according to each sector's needs. Final assembly of the rocket depended on synchronizing these supply chains. When a batch of electrical parts arrived before the metal sections, technicians advanced partial installations and waited for the remaining modules. When fuel tanks were delayed, engines already assembled sat idle in wagons until the flow was restored. This imbalance was constant because the production of each component responded to unstable external conditions. Despite the interruptions and reallocations, the underground factory managed to complete batches of rockets that were immediately shipped to military units. Covered wagons left Nordhausen bound for launch areas distributed across the Netherlands and Western Germany. These trains were escorted because any loss along the route meant a direct delay in the operational use of the weapon. The complexity of this logistical chain demonstrated the industrial burden the program represented. To keep production active, Germany had to redirect resources from sectors already operating at their limits, creating internal disputes and delays that accumulated as the conflict advanced across European territory. When the first batches left the underground factory, the Army organized specialized units to operate the rocket in occupied regions. These units were established mainly in the Netherlands, where wide roads and forested areas made it possible to move equipment without constant exposure to enemy aircraft. Each team included navigation operators, fuel technicians, heavy tractor drivers, and officers responsible for coordinating launch preparation. The launch structure was assembled in areas chosen based on railway access. The rockets arrived in covered wagons and were transferred to special trailers capable of carrying vehicles weighing more than 12 tons across rural roads. These movements required careful planning, as the convoy had to avoid sections where craters or debris could block the route. The preparation process began with assembling the platform. Technicians installed metal rails on the ground to level the equipment that would support the rocket in an upright position. The platform included hydraulic cylinders to adjust the initial angle and allow corrections during attachment of the vehicle to its supports. All of this had to be done silently because enemy units could detect vehicle movement during the night. Once the platform was ready, the team positioned the rocket with articulated tractors. The vehicle was raised by hydraulic systems that placed it vertically, held by lateral supports. From that moment, fueling began. Tank trucks transported ethanol, while others carried liquid oxygen kept in insulated containers to prevent evaporation. Transferring these liquids required extreme care to avoid valve freezing or pump overheating. With the rocket fueled, operators installed the warhead and connected the electrical ignition system. Long cables linked the platform to a mobile cabin where panels displayed pressure, temperature, and the status of internal systems. These instruments were covered with improvised shielding to prevent reflections that might be spotted by aerial patrols during daylight. Before authorizing the launch, the team checked the coordinates set for the target. The rocket had no correction mechanism after reaching the apex of its trajectory, meaning that small deviations in the initial calibration could result in significant differences at the impact point. Operators adjusted gyroscopes and acceleration sensors directly on the platform to reduce the margin of error. When ignition was activated, a white cloud of evaporated oxygen covered the base of the rocket. Moments later, the engine reached full combustion, and the vehicle lifted from the platform at increasing speed. Within seconds, it disappeared into the cloud cover. The team quickly dismantled the area, retrieving cables and equipment to avoid detection by aircraft that might investigate the launch site. Mobility was essential. Because the launches occurred in open areas, teams changed position after each shot. Trucks, tractors, and control cabins moved to another part of the forest or to distant clearings, making it difficult for Allied forces to locate permanent bases. This strategy allowed successive launches without suffering direct attacks during operations. Even with this mobile system, the continuous supply of rockets depended on the long logistical chain connecting the underground factory to the launch areas. Trains had to cross bombed regions, and roads required frequent repairs. These movements determined the weapon's operational pace, influencing how many projectiles could be fired in a single month. The rockets fired from mobile positions reached significant speed while still close to the ground. The main engine operated for less than a minute, but during that interval the vehicle accelerated to values exceeding 4,000 kilometers per hour, creating enough force to continue its journey even after shutdown. This initial phase defined the range and determined the maximum altitude the projectile would reach before beginning its descent. During ascent, internal sensors recorded acceleration and guided small graphite vanes installed directly in the engine's exhaust jet. These vanes moved through actuators that responded to commands from the navigation system. While the engine remained active, this mechanism was responsible for correcting deviations and keeping the trajectory within the parameters calculated at launch. Once the engine shut down, the rocket had already passed beyond the atmospheric density at which aerodynamic surfaces were effective. At this stage, the vehicle continued to climb by inertia until reaching altitudes that could exceed 80 kilometers. This path placed the projectile beyond the reach of any ground-based defense, as radars of the era struggled to track small objects moving at such high speeds. The transition between ascent and descent occurred at the highest point of the trajectory. The rocket rotated slightly due to the absence of thrust and began descending along a ballistic curve. With no means of correction during this phase, it depended entirely on the adjustments made before engine shutdown. Small errors accumulated during ascent translated into differences of hundreds of meters at the impact site. During descent, speed increased rapidly. The projectile re-entered denser layers of the atmosphere, traveling at values exceeding 1.5 kilometers per second, enough to generate intense heating on the external structure. The metal plates covering the rocket's body were designed to withstand this friction, preventing deformation that could compromise the alignment of the warhead. The warhead carried roughly 900 kilograms of high-power explosive. Impact occurred before any sound preceded the projectile's arrival. Its supersonic speed meant that the air displacement boom was heard only after detonation, creating an effect that confused defense teams and hindered civilian evacuation. Accuracy depended directly on calibration conditions. On days with strong winds, operators adjusted motor burn time and gyroscope parameters. Even so, the margin of error could reach kilometers because the combination of speed and altitude made it impossible to control the flight after propulsion ended. The weapon was designed to strike broad areas rather than pinpoint targets. To measure launch performance, technicians monitored data transmitted by radio during the first seconds of flight. These signals included readings of pressure, rotation, and engine status. After contact was lost, teams depended on impact observations recorded by units on the ground located near the affected regions. These analyses served to adjust configurations for subsequent launches. The combination of range, altitude, and speed made the rocket a weapon without equivalent in the German arsenal of the time. It could cross borders undetected and strike distant cities without relying on pilots. This characteristic expanded its use in operations requiring an immediate response, especially when conventional units lacked means to reach targets located beyond enemy lines. Even with these capabilities, performance varied according to external factors. Ignition failures, fueling issues, and imprecise sensor adjustments could completely compromise a launch. The weapon depended on a complex logistical chain and careful technical operation. Each shot was the result of a process involving specialized training and coordination among several teams. The first rockets launched against London revealed how the weapon behaved in a real scenario. The explosions struck residential neighborhoods without any warning because impact occurred before the supersonic boom could be heard. The craters left ruins scattered across several meters, with buildings partially collapsed and vehicles destroyed by the shockwave. Rescue teams struggled to locate survivors as entire structures gave way in a domino effect. The distribution of impacts showed that the rocket did not follow a perfectly predictable trajectory. Areas such as Chiswick, Stepney, and Tottenham were hit on different days, with irregular intervals between each attack. The variation in impact points revealed limitations in the navigation system's accuracy, which depended entirely on initial calibration performed at the moment of launch. The amount of damage increased as more rockets reached the city. The impacts destroyed houses, warehouses, small bridges, and sections of paved streets. The weight of the warhead created a significant radius of destruction, even when the projectile struck open areas. In densely populated regions, the effect was amplified by the proximity of buildings and by the structural collapse caused by air displacement. The units responsible for the launches also began directing rockets toward Antwerp, a Belgian city that served as an entry point for Allied supplies. The choice of this target was directly related to the importance of its port, which received ships loaded with ammunition, fuel, and equipment. The attacks sought to disrupt this flow, striking both urban areas and logistical facilities near the docks. The impacts in Antwerp displayed characteristics similar to those observed in London. The projectile's speed made any attempt at interception impossible, and defense teams could identify the fall only after the explosion had already occurred. The destruction included burning warehouses, twisted metal structures, and vessels damaged by scattered debris. Allied records indicated that, even with a considerable number of launches, the distribution of damage remained wide and unpredictable. Regions near the port were hit on some days, while residential districts suffered impacts on others. This irregularity made evacuation measures difficult, as the weapon followed no defined pattern and could strike any area within its range. The human consequences were significant. Medical teams faced difficulties dealing with multiple injuries caused by collapsing walls, metal structures, and fragments projected by the explosion. The absence of sirens or warnings made it impossible to guide civilians to seek shelter. Many survivors reported having been thrown a considerable distance by the shockwave, even while inside masonry buildings. Local governments responded by reinforcing debris removal teams and creating specialized groups to analyze damage. These groups mapped affected areas to verify the integrity of remaining structures. Since new impacts could destabilize buildings already weakened, streets needed to be cleared quickly to allow emergency vehicles to pass. Despite the increasing frequency of launches, the impact pattern showed that the weapon functioned as an area projectile. It struck entire cities without discriminating specific strategic points. This characteristic defined its practical utility: to cause disruption, wear down civilian infrastructure, and partially interrupt urban and logistical activities, but without the capability to destroy military targets with precision. The underground production facilities managed to maintain a continuous flow of rockets during the final months of 1944. The factories delivered enough units to sustain a sequence of launches, but the number of completed projectiles never reached the figures planned by the High Command. The combination of logistical interruptions, material shortages, and constant personnel relocations limited the quantity of rockets ready for use each week. Although several hundred projectiles were fired at London and Antwerp, the ratio between rockets produced and rockets actually launched revealed the industrial effort required to maintain the operation. Many units were held back for repairs, sensor adjustments, or replacement of components that could not withstand the vibrations of the launch platform. This process increased the time between a projectile's arrival to the teams and its eventual firing. The strategic impact was constrained by the ability to produce rockets at scale. The weapon required aluminum, copper, precision electronics, and liquid fuel in significant quantities. These inputs competed with the production of aircraft, engines, and armored vehicles, sectors already operating at the limits of availability. Each batch of V-2s represented materials diverted from other fronts of the war. Limited accuracy reduced the rocket's military usefulness. It could strike entire cities, but it could not be directed at specific installations requiring concentrated destruction. Ports, bridges, and industrial centers would have needed repeated hits on exact points, something the ballistic trajectory could not guarantee. As a result, the damage spread across wide regions without permanently compromising the Allies' vital infrastructure. The time required to prepare each launch restricted the volume of firings. The teams operated heavy equipment that needed to be transported, leveled, and calibrated before each shot. Even with specialized training, the logistics of moving through the forests of the Netherlands prevented high daily operating rates. The weapon depended on long supply chains and favorable conditions in the field. A comparison between the rocket's industrial cost and the effect achieved in the targeted cities highlights the difficulty of sustaining the program. The high explosive warhead caused significant destruction at the point of impact, but it did not surpass the potential of Allied air raids, which dropped tons of bombs on selected targets in a single night. The V-2 was launched individually and could not replicate that scale of destruction. With Allied troops advancing across European territory, the units responsible for launches were forced to move more frequently. Damaged roads and the loss of railway routes delayed the arrival of new projectiles and made it difficult to maintain suitable firing positions. These delays reduced the frequency of attacks precisely at the moment when Germany faced the most intense military pressure of the conflict. By early 1945, Germany's industrial situation no longer supported the pace needed to keep the program active. Continuous bombings struck production centers, power plants, and railway segments. Each new attack interrupted essential flows, making it difficult even to transport cryogenic tanks needed to supply the remaining rockets. The sum of these factors defined the weapon's real reach during the war. The rocket demonstrated unprecedented technical capability, but it operated in insufficient numbers to alter ongoing military campaigns. Its use remained concentrated in sporadic urban impacts, originating from a logistical chain that struggled against the progressive exhaustion of German infrastructure. As Allied troops advanced through Germany in early 1945, intelligence services began monitoring more closely the movement of technicians involved in the rocket program. Reports indicated that many documents had been removed from Peenemünde and stored in inland areas of the country, mainly near Nordhausen. This relocation showed that the German command was attempting to preserve information before the factories were reached by the front. With the approach of American forces, scientists connected to the development of the A-4 began leaving the underground facilities. Groups moved toward mountainous regions in southern Germany, carrying boxes of technical schematics, test reports, and smaller parts that could be transported by road. This movement occurred in parallel with the collapse of the railway infrastructure, which made it impossible to remove larger equipment from the factory. U.S. troops entered the Nordhausen area in April 1945. Upon inspecting the galleries, they found assembly lines still intact, with fuselage modules hanging from metal supports and engines partially completed. Several projectiles were positioned on internal tracks, ready to be moved but with no possibility of launch. The scale of the installations surprised the units that conducted the initial inspection. American teams immediately began cataloging everything that could be transported. Structural components, fuel valves, electrical systems, and combustion chambers were removed from the galleries and sent to improvised depots in nearby towns. The goal was to gather enough material to reconstruct the rocket in Allied territory and analyze the technology used in Germany. While the United States secured control of the underground factory, Soviet groups advanced from the east toward the coastal areas where Peenemünde was located. The complex had already been partially evacuated, but technical buildings, test platforms, and transport tracks remained standing. The Soviets collected prototype shells, damaged engines, and fragments of control vanes left behind after test launches. The competition between Americans and Soviets intensified in the following weeks. Both powers sent military engineers to examine captured facilities. These specialists sought to understand the manufacturing method, the accuracy of the navigation systems, and the performance of the engine. Each recovered piece was shipped to laboratories in their respective countries, where teams analyzed materials, welds, and technical drawings. The capture of scientists became a priority. The United States organized operations to locate engineers who had worked directly on the program. These groups were found in small towns, often hiding in homes occupied by their own families. After negotiations, they were escorted to zones controlled by the U.S. Army, where they began providing detailed explanations about the rocket's operation. The Soviet Union also recruited German specialists. Engineering teams were transported to laboratories in the central region of the USSR, where they resumed tests based on fragments collected in Peenemünde. This process caused the technical knowledge accumulated during years of German research to be incorporated simultaneously by two future rivals in the space race. The captured materials were reorganized into complete sets. In the United States, military laboratories reassembled engines, hydraulic systems, and navigation sensors to reproduce a functional rocket. From these reconstructions, teams began testing combustion chambers and analyzing the behavior of metal alloys at high temperatures. The objective was to understand every stage of manufacturing and the limits of the original design. The competition for the technology marked the beginning of a new chapter. Components removed from an underground factory in Germany began to influence research programs that would shape the course of post-war rocket engineering. Each country would use this knowledge to develop vehicles of greater range, initiating a process that would go far beyond the original military purpose of the weapon. After capturing the technical material and the teams involved in the German program, the United States organized the transport of the remaining rockets to its own bases. Several projectiles were sent to the White Sands Proving Ground in New Mexico, where military engineers reconstructed complete units using parts collected in Germany. The combination of original components with elements manufactured in the United States made it possible to conduct experimental launches as early as 1946. The first American tests were used to measure the rocket's stability under controlled conditions. Filming equipment recorded the ascent from the moment of ignition to engine shutdown. Data collected by instruments installed in the fuselage were transmitted by radio and analyzed in Army laboratories. These trials helped define flight parameters that would later be applied to long-range rocket projects. The Soviet Union carried out a similar process using material recovered from Peenemünde and factories located further inland. Soviet engineers reassembled engines and navigation systems to create a functional replica of the rocket, later known as the R-1. Initial tests took place in remote regions of the country, where teams analyzed performance, range, and structural behavior during the re-entry phase. In both programs, the focus was on understanding the technological limits Germany had reached. The liquid fuel engine demonstrated the ability to generate stable thrust for long enough to reach altitudes that exceeded known atmospheric barriers. The metal structure withstood vibration and intense heating during descent, enabling engineers to evaluate materials suitable for future, more powerful designs. American interest included scientific experiments that went beyond military use. Some rockets launched from White Sands carried instruments designed to measure solar radiation, atmospheric pressure at extreme altitudes, and brief microgravity conditions. These experiments provided unprecedented data to research institutions that previously lacked access to vehicles capable of reaching such heights. The Soviets concentrated efforts on adapting the rocket for long-term programs. The initial replica served as the basis for more advanced models that incorporated improvements to the propulsion system and structural modifications to support heavier payloads. Each evolution brought the Soviet program closer to projects requiring intercontinental range, a goal that would become strategically important in the following years. The knowledge transferred by German specialists directly influenced the technical teams of both countries. Projects conceived during the war were revised, expanded, and reinterpreted in new laboratories. Navigation systems were replaced with more precise versions, and engines received adjustments to increase efficiency without altering the fundamental principles inherited from the A-4. As testing progressed, the United States and the Soviet Union began to diverge in their approaches. The Americans prioritized scientific experiments and the gradual development of larger vehicles, while the Soviets concentrated resources on creating versions capable of carrying heavy military payloads over greater distances. This difference set distinct paths for the space programs that would emerge in the following decade. The presence of fragments of German rockets in American and Soviet laboratories symbolized the end of one phase and the beginning of another. Each country used the captured elements to solve technical challenges that had limited their own programs before the end of the war. The V-2 ceased to be merely an operational projectile and became a direct reference for technologies that would go far beyond the original context of its creation. The V-2 passed through the war as a project that consumed immense resources, imposed unprecedented industrial challenges, and ultimately served as the foundation for rocket programs that would shape the following decades. Its structures, engines, and testing methods migrated to American and Soviet laboratories, where they ended up shaping the first vehicles capable of reaching space. What began as a long-range weapon became the starting point for technologies that would surpass military boundaries and open the way for orbital exploration. If you want to follow other episodes that detail decisive technologies of the Second World War and their post-war developments, subscribe and activate notifications. Each new video explores in greater depth a piece of this period in which science, war, and industry intersected in decisive ways.